students. So here we are in chapter 7, which is solids, liquids, and gases. And we're going to talk mostly about gases. Now, solids, liquids, and gases were reviewed in chapter 2. So some of this stuff is repeat, but a lot of it's new, and that means calculations. But first, before we get to math, let's just go ahead and review a little bit of what we know about the properties of solids versus liquids versus gases. Now, in our solids, what we have is we have atoms that are very close together, and they're in a fixed spot and they don't slide past each other. They just stay right there and they like to snuggle together. And then in liquids, we have atoms or molecules that are very close together, but they have enough space between each other to slide past each other. And that allows fluids to flow. And fluids actually include liquids and gases, but in everyday speak, we usually refer to liquids as fluids. And I'll get to fluids as liquids and gases in a little while. But anyways, back to the liquids, there is enough space between the atoms or the molecules so they can slide past each other, but they're still really, really close. And then we have gases. So the atoms or the molecules in gases are pretty far apart and they bump into each other, but they're not attracted to each other, so they just go their merry way once they've bumped into each other. They're like, hi, hi, and then they go on their merry way. Okay, so what else do we know about gases? Well, gaseous molecules, because they're moving around really quickly and they're really small and they're not attracted to each other very much, what they do is they bounce off of each other and they bounce against any kind of container that they're in. So because they're moving around and bouncing off the sides of the containers, what we say is that they take the shape of their containers. So what they do is they expand to fill their containers, so they use up any empty space. And this means that they have an indefinite shape, so they do not have a definite shape. They take the shape of the container and they have an indefinite volume. So if you give them a little bit of space, which is a small volume, they'll take up a little bit of space because they can be compressed because there's a lot of nothing between them. But if you give them a large space, they'll gladly zip around in that large space and take up the whole space. They have an indefinite volume. So again, because they have a lot of space, we can compress them, and you will see that with tanks of oxygen, which people with emphysema and other breathing disorders might carry around with them. And this gives them a very low density. So there isn't very much mass in the amount of space that they're taking up because, first of all, our gas molecules are really small compared to other molecules, and there's a lot of nothing there, so you don't have a lot of mass in that space. So that means that they're 1/1000th the density of your equivalent liquid or solid, remembering that liquid and solid atoms or molecules are really, really close together. So you have a lot of mass and a little bit of space with those states. And right here it says that gases are also fluids, which makes us go, huh? Because in real life, we think of liquids and fluids as the same thing, but fluid means that it can flow. So if we think of natural gas, which is what we use to light our our stoves if we have gas burners, or if we have a gas water heater or a gas dryer in our house. This is the gas that we use, and it's mostly methane. And methane is CH4, and then we've got some other hydrocarbons in there. But what happens is that this gas flows through the pipe and it goes into our house. So yes, gases are fluids too, they flow. They also undergo effusion and diffusion. Now, most of us have heard of diffusion, and specifically diffusion of water, which is called osmosis. So maybe we're sitting here thinking, what on earth is effusion? Well, I have a slide for that. Yay! So what happens with diffusion is we have a couple of gases, and one is on one side of the container and the other is on the other side of the container. And we open up that little spot right there, and naturally, so spontaneously, we'll get movement of gas 1 into the chamber where gas 2 is, and gas 2 will spontaneously move into the chamber where gas 1 is, until we get a nice constant concentration of both gases on each side. And we have reached a point that we call equilibrium. So the rate of gas movement going into chamber 2 is the same as the rate of gas movement of the gases going into chamber 1. And yeah, that's diffusion. Now, effusion isn't all that different. We just have nothing on one side. So right here it says vacuum, which just means there's nothing there. It doesn't mean a vacuum cleaner like a Dyson or a Hoover. It means nothing. And then you open it up and the gas will spontaneously move into the other side until you have constant concentrations of that gas on each side. And then that brings us to another part of gas, very important, which is pressure. So what is pressure? Well, if we look at the mathematical equation for pressure, what pressure is force divided by area that force is going to be distributed over. We can also say that pressure is caused by the collision of atoms or molecules with a surface or with the walls of a container. So right now, as you sit here listening to me, you're feeling a lot of pressure. And maybe it's from chemistry class, or maybe it's because the air molecules are bouncing off of your body, and that's making you feel the pressure of the air in the room. So if you look down here, we can see the other way we can define it as the collisions of molecules or atoms with the side of a container. So if you get more hits, you'll have more pressure. Now, the SI units, so the international units for pressure, that's a Pascal. And what a Pascal is a Newton divided by a meter squared, which sounds really strange, but a Newton is a unit of force. And the meter squared right here just means meter times meter, which equals meter squared. And when you think about area is length times width. So if this width right here was 1 meter and the length was 2 meters, the area would be 1 meter times 2 meters, and 1 times 2 is 2, and meters times meters is what? It's meters squared, because when we have an exponent and we are multiplying things with exponents, what you do is you add the exponents. So 1 plus 1 would give us 2. I know that sounds kind of funny, but that's how the math works with exponents. All right, so pascals. Pascals are like any other metric unit. You can have pascals or kilopascals or millipascals or micropascals. But what we'll see most often is pascals and kilopascals. And where we'll see pascals are when we have 101,325 of them, equaling 1 standard atmosphere or 1 ATM. So you guys will see ATM a lot in this chapter. And what an ATM is 760 millimeters of Hg. What's Hg? Does anyone remember? Like you're going to all be talking to me right now. It's mercury. That's right. You said that, right? Of course. And millimeters of mercury are the same exact thing as torr. So 1 torr is 1 millimeter of mercury, and why that is, we'll get there in a little bit. And then another unit of pressure that Americans are used to is PSI. That is pounds per square inch, and we will see that on our bike tires and our vehicle tires. So just in case you weren't listening to me, right down here is a little chart of the different pressure units you will see. Now, one of the difficult parts of this chapter is not the math, because the math and algebra for these problems is actually pretty easy. What is difficult is keeping track of all the variables and all of the units. So all of these plus Pascal, plus kilopascal, plus inches of mercury, those are pressure units. And if you see a number with one of those units written after it, you have to be able to say, okay, that's a unit of pressure. And you have to be able to separate it from units of volume, like milliliters or liters, and units of temperature, like degrees Celsius, degrees Fahrenheit, and in Kelvin, because we're going to be working with all of those. All right, moving on. So where do we see pressure in everyday life besides chemistry class? Well, if you've ever driven up a mountain, or if you've been on a plane ride, what you've experienced is your eardrums popping. And that's because as you drive up the mountain, or you ascend up into the air, there are fewer gas molecules up there. And what happens is that there's less pressure on this side of your eardrum because there's fewer gas molecules or fewer air molecules hitting that side of your eardrum. And the air on the inside of your ear still is full of oxygen, nitrogen, all the other elements, all the other molecules that are in our air. It's still full of those molecules that are pressing on the inside of your eardrum, and that pushes the eardrum out and it causes you pain. Now, what happens is you swallow or you yawn, and some of this air goes out and it equalizes the pressure on each side of your eardrum, and it gives you relief. And you feel that little popping sensation and you can hear again, and you're like, oh, thank goodness. Or you chew gum. That's another way to do it. Okay, so how can we change our pressure? Well, if we're looking at the two jars right here, what you can see is that if you add more gas atoms or molecules into a container, what will happen is you'll get a whole lot more of these guys hitting the sides of the container, because more gas molecules means more hits, which means more pressure. The other thing you can do besides adding more gas molecules to a container is to decrease the volume. So if we look at this example right here, it says that the pressure inside this container is 100 kilopascals and the volume is 6 liters. So we've got these gas molecules bouncing around and hitting the sides of the container, causing pressure. And then if we compress the gas to 3 liters, so we have the volume of the container. So inside here, there's half the volume now. We went from 6 liters to 3 liters. And what you can see is that your pressure increases from 100 to 200 kilopascals because those gas molecules inside that container have less space to move around. So they're hitting the sides of the container more often. And when you get hits on the sides of the container, that is what? That is pressure. That is called pressure. And then if we decrease the volume even more to 2 liters, what we can see is that our pressure increases even more to 300 kilopascal. So those molecules are hitting the sides of the container a whole lot more. And they're getting a little bit angry because people, when they get too close to other people and other people are encroaching on their personal space, we get a little bit upset and crabby. At least I know I do. And the pressure builds. And then I got to get out of there. And that means we're going to the next slide. So we just talked about the units of pressure, but how did we figure this out? Well, there is this guy named Evangelista Torricelli, and he lived during the 17th century. Now, the 17th century is not the 1700s. The 17th century is the 1600s. I know that sounds really weird, but that's just how it works. Okay, so he was the one that first described measuring atmospheric pressure with this thing called a barometer. And yes, I know that it's debated whether it was Torricelli or it was Gasparo Berti or it was Galileo or it was Descartes, but who is given credit for it is Evangelista Torricelli. So he's the guy that gets on my slide. Okay, so barometer. Barometer came from baro, meaning weight, and meter, meaning measure. So what Torricelli did was he got a little glass tube and he put some mercury in it. And remember, mercury is our liquid metal. And then he put it in a little dish that was filled with mercury also. And so he inverted the tube. So the opening to the tube is down here somewhere. And the mercury slid down into the tube and it created a vacuum up here. And again, I don't mean a Dyson or a Hoover. What I mean is there's nothing there. It's a vacuum. And what happens is our air molecules, so our O2 and our N2 and our argon, and because we live in Riverside, we've got all kinds of other crapola in our air, is hitting the top of that mercury in the dish. It's hitting that surface area. It's putting a force against it. And it's keeping this mercury in here up a certain distance. So at sea level, the average barometric pressure is about 760 millimeters. So that's 760 millimeters of mercury, or 29.92 inches of mercury. And what Torricelli noticed was that on different days, the height of the mercury was a little bit different. So as the barometric pressure changed every day, the height varied a little bit. And what he also noticed is that he could predict storms coming. So when you get a low pressure system coming in, that's indicating that a storm's going to happen. So if you watch a weather report, if a storm is coming, they'll say there's a low pressure system on its way. When we have a lot of heat and we have clear skies during the summer, and The weather reporters on there telling us about how it's going to be 110 degrees. They'll say a high pressure system is sitting over Southern California and not moving. And that means we're all sitting inside with our air conditioners on going, when will August be over? So this was our first barometer, what it looked like. Also, I promised that I'd talk about millimeters of mercury and torr and why they are the same thing. So back here, that's where I said that we have 760 millimeters of mercury, which is exactly the same as 760 torr, which is 1 atm. So here's the slide where I'm going to tell you that 1 millimeter of mercury is equal to 1 torr with a small t, and that's after Mr. Torricelli. And that's why they're the same thing. Now, what does this look like in real life today? Well, here is an aneroid barometer, also called an analog barometer. So anytime you see a little needle, that's an analog piece of equipment. And down here you guys can see inches of mercury, which we usually write as inches of mercury instead of INS, but that's how that one is displayed, so we'll go with it. Now here is a digital barometer, something you might see today if you're not using the one on your phone. So a lot of phones have it, or weather apps will definitely have it. And you can see down here that we've got inches of mercury. So we've got 29.31 inches of mercury at that time of day and at that temperature. There's a whole lot of other interesting information there, but I'll let you guys take a weather class to talk about all of that. Okay, so moving on to some gas laws. So we have to talk about Boyles Law, Charles Law, and Gay-Lussac's Law. This means math is coming. Oh no! All right, so our first gas law is Boyle's Law. And Boyle's Law talks about the relationship between pressure and volume. That says that the more pressure we're under, the larger the volume of Doritos that we eat, right? Just kidding. All right, so who thought up Boyle's Law? Well, it was Mr. Boyle. And Mr. Boyle lived in the 17th century. So see how it's the 1600s? Yep, that's how it works. And he was born into an aristocratic Irish family, which means he was rich, which means he had a lot of time to sit around and think about things like gas laws. That's how it worked back then. It was the people who had time that were allowed to be philosophers and scientists, and the people who had time were the rich people because they didn't have to use their time working. All right, so what happened was he became interested in medicine and science because of all the science that Galileo did, and this guy wanted to study chemistry. And he was also one of the founders of the Royal Society of London. And if you want to learn a little bit more about the Royal Society of London, you need to take Chem 17 with me, which is a history of science, which is really fun, and you're going to have a good time with it because you're going to sign up for it, right? Right. Okay. So he wrote a lot about science, philosophy, and theology because back then, science, philosophy, and theology all went together. So these rich guys with a lot of time on their hands, they would think about things, they'd do little experiments, they'd come together, and they'd talk about their ideas, and if they had any ideas which they wanted other people to believe, they would bring along some evidence or an experiment to show everybody, and then they'd all debate the results. But more on that in Chem 17. Now, what did Boyle say? Boyle said that the volume of a gas is inversely proportional to the pressure. Now, we've got volume and pressure there. We knew we were going to deal with, but that inversely proportional part of it. What is inversely proportional? Well, it means if one thing goes up, another thing goes down. Or if the original thing went down, the other thing goes up. So if one thing goes up, the other thing goes down. Okay? So if you have a decrease in volume, meaning that your gas is getting squished, what's going to happen is your pressure is going to increase. And why is your pressure increasing? Well, if you squish your gas, it's going to be hitting the sides of the container a whole lot more. And when you have atoms or molecules hitting the sides of a container, that is called what? Pressure. All right, when you increase the volume, so you give your gas a whole lot more space, and the molecules can spread out. They don't hit the side of the container as often because they have a lot of room. So it takes them a long time to hit some other gas molecule or hit the side of the container. So if you increase the volume, what do you do to the pressure? You're going to decrease your pressure. So increase volume, decrease pressure. Decrease volume, increase pressure. And what this looks like on a graph is this. So you can see that as we decrease the volume, so we go from 4V to 1V, so we decrease our volume, what happens to the pressure? It increases. So right here turn back around. I'll just write it here. Increase in our pressure. Now, if we increase our volume, what we do is we decrease our pressure. So we get this lovely curve. So the curve is like that. What we also get from this information is Boyles Law equation, which says P1V1 equals P2V2. So right here we have our initial pressure and volume, and right here we have our pressure and our volume after our change. And they need to equal each other. So say your initial pressure is 3, maybe it's 3 atm or 3 inches of mercury or whatever pressure unit you want. And your original volume is 5 milliliters or 5 liters or 5 ounces, fluid ounces, whatever you want. Well, what's going to happen is that this side of the equation needs to equal this side of the equation. So if you change your volume from 5 to 3, so say you compress your volume from 5 liters to 3 liters, your pressure is going to need to do what if you squish your gas? Your pressure is going to need to increase. And since both sides of the equation need to equal each other, the pressure is going to change to 5. So you're going to have 15 on each side of the equation. And don't worry, we'll do a lot of these problems. Now, what you guys are going to have is 3 variables, and you're going to need to solve for one of the variables. So right here, what you have is all of the equations rearranged for you. Just in case you don't want to do some algebra that day, you can just whip out this slide and go, okay, V2 equals blah, 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 blah. For the rest of us who want to practice our algebra, because that's a good thing to practice, we're going to go ahead and do the algebra on it. And here we are! Yay! We're in the problems section. Okay, so number 1 says you have a 2.5 liter cylinder of gas under 100 kilopascals of pressure. If you compress the gas to 1 liter, what will the new pressure be? All right. We've got 3 givens there, and what on earth do we do with them? Well, let's look at our units. Liters, that's a unit of what? Is that pressure, volume, or a temperature? That's volume. And that volume of gas is under 100 kilopascals of pressure. Now, right there, it told you that's a unit of pressure, so that's a P. And it says if you compress the gas to 1 liter, so there's another volume, so we have another V. So one of them must be V1 and the other one is V2. Now, this P right here goes with this V. So if those go together, then if V1 is V1, then your P has to be P1 because that's a set. So it goes together. Now that says, what will the new pressure be? So we're looking for a P, and we're looking for a P when volume is V2. So this must be P what? P2, because it's that pressure when you have volume 2. So if you have V1, P1, V2, P2, you should have an alarm bell going off in your mind saying, aha, I am going to use the equation P1 V1 equals what? Equals P2 V2. Also, we haven't seen any other equations yet. And don't worry, we will see equations. Okay, so what we want to do is we want to list our variables so we can just organize our thoughts. So P1 is what? P1 is 100.0 kilopascal. That is right here. And V1 is what? V1 is 2.50 liters. Remember, kilopascal is a unit of pressure and liters is a unit of volume. Now, what's P2? We don't know because the question says, what will the new pressure be? Now, what's a V2? V2 is 1 liter. Okay, so we've got all of our variables listed and we know what our unknown is. Our unknown is P2. So we need to solve this equation right here for P2. So I'm going to go ahead and write it one more time right here. Now we're going to use the magic of algebra, which says that variables can move diagonally across an equal sign. So we want to get P2 by itself, so we want to take V2 and we want to move it down there. So remember, variables can move diagonally across the equal sign, and that's legal. Okay, and we don't have to write the 1 down there because we know the 1's down there. And that is equal to P2, or P2 over 1, either way. Now, most of us like for our variable that we're solving for to be on the left-hand side, so I'm just going to switch this around because that's legal to do also. So P2 equals P1 V1 over V2. Now, if you wanted to do it the traditional algebra way, that's fine too. So let me just go ahead and write in V2 right here. And what you would want to do is you would want to multiply both sides by what you want to get rid of, or divide both sides by what you want to get rid of. And you would do exactly the same thing as the magic of algebra, except for you would be writing V2 another time, and then that would cancel out. And what you would end up with is exactly that. Okay, so what we do is we plug and chug now. So P1 is what? P1 is 100.0 kilopascal, and we're going to multiply that by V1, which is 2.50 liters, and we're going to divide that by V2, which is 1 liter. And we're going to say to ourselves, okie dokie, which unit can I cancel out? I can cancel out liters, because anything divided by itself is what? Is 1. So those cancel out, and I'm left with kilopascal for my unit. Now looking at what I'm solving for a pressure. Does a unit of kilopascal being left over make sense? Yes, because kilopascal is a unit of pressure, and I'm solving for a pressure. So far we're making sense. Now, if you put this into your calculator, whiz bam bang, you're going to figure out that what you have is 250, and we'll put a little dot there to indicate we've got 3 sig figs kilopascal. Okay, so 3 sig figs there, 3 sig figs there, and we've got how many there? We've got 4 sig figs there. So I go with the lowest number, which is 3, and we can see that we have 250 with a decimal right there, kilopascal. So little k, big P, little a. Alrighty, number 2, you have a 10-liter container of gas under 505 torr of pressure. If you increase the pressure to 1155 torr, what will your new volume be? Okay, so since we are in the Boyles Law part of the lesson, we can assume that we're doing P1V1 equals P2V2, but let's make sure we've got a couple of P's and a couple of V's. All right, so 10 liters. Liters is a unit of what? Of volume. So that's a V. And the gas that's in that 10 liters has 505 torr, and it says of pressure right there. So that must be a P. And then we're going to increase the pressure to 1155 torr. So we've got another P here. So when we have two different ones, we have to have a P1 and a P2. So P1 and P2. Now the volume that goes with P1 is 10 liters, and if P1 is P1, then the V that goes with it must be what? B1. Okay. We also are being asked for a new volume, so that has to be a V. And if you have V1 and another V comes along, the next V is probably what? It's probably V2. And also that V2 has to be the volume that corresponds with P2. And it does. It says we increase the pressure to 1155 torr. When we do that, what is the new volume? So 1155 and the new volume go together, so they're the 2's. All right, so we're going to list our variables just to organize our thoughts. P1 is what? It's 505 torr. And V1 is what? It's 10 liters. P2 is 1155 torr. And V2, we don't know. That's what we're solving for. Okay, so here's our equation. And we're solving for V2. So I'm going to move that over here. And we have P1, V1 equals P2, V2. And let me erase this guy right here so I have some more room. Okay, so we're solving for V2, so we take P2 and we move it diagonally across the equal sign, right there by that number 1 that we don't see but we know that's there. And that's going to give us that V2 is equal to P1 V1 over P2. So I moved the P2 down into the denominator, and then I just switched it around so we have the variable that we're solving for on the left-hand side. Again, you guys can do that with a traditional algebra, where you would divide both sides by P2. So you'd say, okay, I'm going to divide this side by P2, and I'm going to divide this side by P2, and then those cancel out. And then I get V2 is equal to P1 V1 over P2, which is exactly the same as what we just did. Okay, plug and chug time. So P1 is 505 torr. We've got 3 sig figs there, multiplied by V1, which is 10 liters. We've got 3 sig figs in 10 liters. And then we have P2 on the bottom, which is 1155 torr, 4 sig figs. So we have 3 sig figs times 3 sig figs divided by 4 sig figs. So our answer is going to be how many sig figs? 3 if we're using significant digit rules. And if you put this into the calculator, what you're going to get after you cancel out torr and are left with a unit of liter, which makes sense because you're solving for volume, and liter is a unit of volume, is 4.37 liters.